Guess what? Those are buffers. And then we're going to talk about what buffers are. And guys, that was the important thing that nobody explained to me in high school or college. In order to understand buffers, you've got to understand the common ion effect. And if you don't understand the common ion effect, you can't do buffers. But once you understand the common ion effect, you actually understand buffers. You just don't understand what it is that makes them a buffer. And the connections are really easy. So guys, again, today we're only going to do half of this. We're going to do common ion effect, and then we'll put that in the context of buffers on Monday. You get the idea? Okay, so guys, grab calculators, grab note-taking materials. We are going to do some ice boxing. And guys, if you're resistant to ice boxes, you got to understand that you are going to get really, really good at these in this. It's all we're going to do. And as a matter of fact, not only is it all we're going to do, we are actually going to add 2 more letters to the ice box, and we're going to turn them into iRace boxes. So you need to get over your resistance to this if your belly aching was actually you being serious about not liking this, because like it or not, you're going to do a lot of them. So guys, join me in this thought. I don't know that you necessarily need to write it down, but you'd better be able to think about the answer. And guys, the question is this. We understand from the last unit that Le Chatelier's principle allows us to make predictions about how equilibriums shift when we change the concentration of reactants or products. And guys, just in review, you remember Le Chatelier's principle is never the answer to the question, right? When we talk about shifting equilibria, we've got to talk about it relative to rates. You can use Le Chatelier's principle to help you understand what's going to happen, but it's never the reason why. The reason why is always relative to rate. So guys, with that said, regardless of how you think about it, what's the answer to the question? So it says this. Le Chatelier's principle says that increasing the concentration of the products in a reaction will have what effect on equilibrium? Which way will the equilibrium shift? To the left, right? So the idea is if we've got reactants and if we've got products, and if we add product, same side does the opposite, opposite side does the same. If products go up, reactants go up. We can think of that as shifting the equilibrium to the left. We can think of that as favoring reactants. However you think of it, guys, the answer is it shifts to the left. So now what we need to do is we need to take this answer and let's apply it to the dissociation of acetic acid. So guys, go ahead and write this down in your notes. Write out, well here, I'll give it to you. Well, no I won't, you do it. But make it big. And guys, what I would encourage you to do is skip down multiple lines. Because guys, this is going to be the context in which you are going to understand the common ion effect. This is really proving to be problematic to not have the notes, because it would be really helpful for me to get a sense of how to use board real estate. You know what? Hold on a second. I'm going to see if I can hack my website and get it to cough up my notes. Go here, and go here, and go here, and go here, and there, and this, and go. Oh, look at that. Okay. All right, so guys, I think what we're going to do is we're just going to sort of freeform this conversation, and then we can come back and look at the answers. And we'll see how my board's doing. So guys, what does the dissociation of acetic acid look like? Guys, it looks like this. We've got acetic acid, and when that dissociates, we understand that it does it weakly. You may remember the idea that we said whenever we write out dissociations, we will always do this putting the conjugate base first. You good? Okay. So did we already do the math where we figured out the percent ionization for this? Didn't we do that? Wasn't it like 90, wasn't it like 1% or something? Let's call it 1%. So guys, what we're talking about here is vinegar, right? And we understand that vinegar is acetic acid. We understand that vinegar dissolves, acetic acid dissolves, but some of it dissociates. You may even remember the Ka value for this is 1.8 times 10 to the negative fifth. And we found out that in a vinegar solution, it was like, just using round numbers, 99% this and only 1% these two. You good with the idea? Okay. So now, guys, what we want to do is let's now talk about the common ion effect. So imagine that you've got a bucket of vinegar. And the vinegar has already reached this equilibrium, and we've got a lot of unprotonated acetic acid, we've got a little bit of acetate ion, we've got a little bit of hydrogen ion. Now guys, the question is this: what happens if we come along and if we add acetate ion to this solution? What is that going to do to the equilibrium? It's going to shift it to the left, right? That's what we established in the first thought. So guys, that is going to shift the equilibrium to the left. Are you guys all sold on that idea? Now let me ask you another question. And it's all coming back to this, adding the acetate ion. First of all, this. What could we physically add to a bucket of vinegar to make this happen? Say that I should do this. If I were to hand you a bucket of vinegar, and if I were to send you into my stock room and say, all right, guys, go do this. Anything in the stock room is fair game. What would you grab off my shelf? Go ahead. Why sodium acetate? Good. So guys, the first thing you've got to understand is that acetate doesn't exist by itself. So we need a salt of acetate. But Spencer wisely chose sodium acetate. Guys, given what you learned 2 times ago, why is sodium acetate a wonderful choice? Exactly, because the sodium is a worthless conjugate acid, and it's not going to do any chemistry towards the water, and it's just going to sit there as a spectator. So what would be other acetate salts that we could grab? Well, we could grab lithium acetate, sodium, potassium, rubidium, cesium, calcium, strontium, or barium. Any of those would be wonderful acetate salts to stick in there, because remember, all of these are the conjugate acids of the strong bases and therefore worthless. See what we're saying? So guys, let's say that we chose sodium acetate. So we come along to our bucket of vinegar and we throw a handful of sodium acetate into the bucket. What's going to happen to pH? Let's do this. What was the pH before we threw in the sodium acetate? Less than 7, because it's acidic, right? So guys, what is going to happen to the pH when we throw in the sodium acetate? Why will it go up? Right. So guys, what is pH a measure of? Hydrogen ion concentration. It is a measure of how much of this there is. And so when we throw in sodium acetate, that increases the concentration of acetate. That shifts the equilibrium to the left. So what happens to the amount of protons? It goes down. And what does that do to the pH? It goes up. Do you get the idea? That's the common ion effect. So guys, why do we call it the common ion effect? And the answer is, we have taken a weak electrolyte, like acetic acid, and we have added to that weak electrolyte a salt that has an ion in common with the weak electrolyte. And guys, the bottom line is this. What does that common ion do to the strength of this acid? Does it make it weaker or stronger? Why weaker? Because the pH goes up. But guys, why does it make it weaker regardless of pH? What does it do to the equilibrium? Shifts it to the left. And what is the measure of the strength of this acid? The ability of it to do this. So guys, if the ability to do this is representative of the strength of the acid, then adding the common ion drives the equilibrium to the left, making the acid weaker. Do you get the idea? And guys, it's important that you understand that not just in reference to acids, because slightly soluble salts do this as well. And we're going to talk about that at the end of chapter 17. So guys, you've got to understand the common ion effect, not just in the context of acids and pH, but more generally in the context of any weak electrolyte. So guys, let's summarize. So let's say it and then let's write it down. So common ion effect is this. Adding a salt that has an ion in common with a weak electrolyte. So let's write that down. So guys, what is the common ion effect? It is adding a salt that has an ion in common with a weak electrolyte. That could be a weak acid, that could be a weak base, that could be a partly soluble salt. So guys, again, the common ion effect is adding a salt that has an ion in common with a weak electrolyte. And then guys, bottom line is this. What does adding that salt do to the strength of the weak electrolyte? Does it strengthen it or weaken it? Weakens it. And you need to include that in your notes as well. Adding the common ion weakens the strength of the weak electrolyte. Be that an acid or a base or a weak, slightly soluble salt, it weakens the strength of the weak electrolyte. Yeah?
So the common ion that you add will be like the conjugate every time?
Yes. Yeah, well, every time is tough because what we're going to do at the end of this is we're going to talk about things like magnesium hydroxide. There we go. Magnesium hydroxide, which breaks into this. And so the conjugate acid is magnesium ion. And then the funny part is the people from Epson are coming tomorrow morning to ask me what I think of their board. Okay, you can do that. Apparently it matters where I stand. No, it doesn't. So your question, Jared, was, will it always be, how did you say it? And so we've always got conjugates, right? So these things, although we don't think of them as being conjugates when we think of slightly soluble salts, but I think when you think conjugates, you'd be thinking of this rather than that. And the answer is no. Like, for example, we'll talk about the solubility of magnesium hydroxide in basic and acidic environments. And then our common ion effect is actually relative to the hydroxide and not relative to the magnesium. So it can be either of the ions. So we could even talk about that relative to this. What would happen if we added hydrochloric acid to vinegar? So hydrochloric acid would be a huge source of protons, and that would also drive the equilibrium to the left. Of course, the pH would still go down because the protons would drive that down, but the dissociation of acetic acid would decrease. Does that work?
So that would be a common ion effect?
It would be the common, yeah, it would be the common ion effect.
But that doesn't weaken?
It does. So let's go back and say that again. So if we have this equilibrium, so disregard everything down here in red. If we have this equilibrium, so a bucket of vinegar, right? And if we dumped HCl into the bucket of vinegar, the HCl, as we know, it is a source of protons. And that would cause this to go up, which would still do this, and decrease the strength of the acetic acid. It would...
Because there'd be more acetic acid substances.
Exactly. It would cause less of this to break apart because some of these, thinking about rate, some of these additional protons would grab a hold of acetate ions and convert them back into unprotonated acetic acid, which by definition would make the acetic acid weaker. That said, the pH would still go down because all the protons are in there from the hydrochloric acid, but technically it would still make the acetic acid weaker. Go ahead, Jim. Sorry, Gavin, go ahead.
So the common ion effect doesn't necessarily mean the pH goes down.
Exactly, and that's where I was really trying to go with Jared's question, that when we talk about the common ion effect, frankly, we're going to talk about buffers. And when we talk about buffers, we track pH. And so 90% of the time, we're just going to follow protons because that's what we can see with the pH meter. But we're understanding that as Jared got us thinking, we can add either of those ions and it will drive the equilibrium to the left. So, but that said, typically we'll add the conjugate base of an acid or the conjugate acid of a base. Yeah.
So when we add a base to this hypothetical bucket of acetic acid,
Mm-hmm.
would that increase wouldn't really increase, would it have the common ion effect?
It wouldn't. It would shift the equilibrium. So the question is, what if we add a base? So if we were to add a base to this, it would tie up protons. And that would decrease the concentration of protons and shift the equilibrium to the right. So it would affect the equilibrium, but it is not an example of the common ion effect because you're not adding an ion in common, you're removing an ion by adding a different ion. So it wouldn't be an example of the common ion effect. So guys, let's use this then as, can we go forward and summarize? Okay, so we just answered these 3 questions. 4. So first of all, we understand that adding the acetate ion would shift the equilibrium to the left. We could do that by adding sodium acetate. This would decrease the strength of the acid and increase the pH. Are we good with those ideas? Okay, so guys, this all then comes down to the common ion effect. Now, we've already defined it in our own words, but check to see if what you wrote down supports this idea. It says the dissociation of a weak electrolyte is decreased by adding to the solution a strong electrolyte, like sodium acetate, that has an ion in common with the weak electrolyte. Now guys, the one thing that we left out, and we're going to be very, very thankful for this quickly, the one thing that we did leave out is this idea. When we add something to our weak electrolyte to create the common ion effect, the thing that we will be adding will always be a strong electrolyte. Sodium acetate, it completely dissociates. Guys, imagine if you were to add a salt to vinegar and the salt that contained acetate was only slightly soluble. Then you'd have an equilibrium impacting an equilibrium. That's your junior year in college. Yeah, thankfully we don't have to go there now. We'll let your PChem teachers explain that to you later. Because that requires calculus. Because you have a rate that depends upon a rate. And we don't have to go there. Yeah, exactly. So guys, are you good with these ideas? And can you sign off on that final expression? You're all okay? All right. So then guys, what we're going to do is this. We are going to leverage this and we're going to do some ice boxes. Figure this out. What is the pH of a 0.3 molar acetic acid solution? Bless you. Okay. I'm not taking a picture. I'm looking at my notes. I know. Oh yeah, yeah. So the guys, the Ka So the Ka of acetic acid is 1.8 times 10 . I want my board back. I guess the reality of it is my board cost about $1,100 and this stupid thing cost $4,000. I could put it on eBay and just get a new board. So guys, I'm going to just sort of start solving this on my own so that we have an example to look at. So did you guys get 2.63? Oh, good. Okay, so I guess that wasn't too painful. Questions? We're okay with the math? We're okay with the icebox structure? That's okay? Okay. So, guys, this is, right, chapter 15. This is the stuff that we learned to do as we were approaching how to study equilibrium systems. And I hope we've become proficient with this. And from looking at your test, frankly, it seems as if most of you have. But now, guys, what we've got to do is we've got to take this, and now we've got to apply this same mathematical thinking in the context of a buffer. So, making sure I click carefully so I don't do anything crazy. So, guys, what we're going to do now, and can you kind of mentally picture what we're talking about here? We just figured out the pH of basically the vinegar that you buy in a big old gallon jug at Smith's. So, now the question is this. What if we take that gallon jug of vinegar, and the aspect ratio on this change, let me move this down here. What if we take that gallon jug of vinegar and we throw in enough sodium acetate to make this solution also 0.3 molar in sodium acetate? Do you see how that's an example of the common ion effect? You okay with that? And what will the pH be relative to our previous number? Higher or lower? Higher, right? The pH is going to go up because the common ion effect will weaken our already weak acetic acid. So guys, the question we understand conceptually, now we've got to figure it out mathematically. And how are we going to do that? And of course, guys, the answer is we're going to do another icebox. So let's do this one together. So guys, what we are doing now is we are applying the icebox convention to allow us to figure out the pH of something that is an example of the common ion effect. So guys, it goes like this. You know what? I'm going to switch colors. How do I do that? I want to switch colors without switching slides because I want these to be in order. Okay, so let's try this now. Come, where? Really? Okay, we did that. There you go. Okay, so common ion effect. Again, guys, I would strongly encourage you to put the conjugate base first, and then the protons, and then we've got icebox. And now, guys, let's talk about how this icebox changes now that we have something that is exhibiting the common ion effect. So, guys, as previously, we have got an initial concentration of acetic acid, and that would be 0.30 molar. Now, up until now, what have we done with the concentrations of our products? They've just been zeros, right? Not anymore. What changed? We now have a source of product ion. So guys, as we can read, we are adding sodium acetate. That sodium acetate becomes a source of free acetate that exists before the acetic acid even falls to equilibrium. So, and conveniently, it's the same molarity. You'll see why that's important in a minute. We now have an initial concentration of acetate ion that is not the product of the dissociation of sodium acetate. Now, guys, what is our concentration of protons? It's 0. That is still 0 because we are assuming that this acetic acid is not broken apart. Again, we were comfortable with the idea of having 0 acetate ion. Now we realize we've got some acetate ion, but it doesn't come from the acetic acid. It comes from the salt that has an ion in common. Now, guys, how does it go from there? Well, now this system reaches equilibrium. So as it reaches equilibrium, this will go down by X. What will happen to our acetate ion? It will go up by X, but no longer does it start at 0. Now it starts at 0.3 and goes up by X. And this goes up by X. So guys, our new equilibrium concentrations then will be given by 0.30 minus X, 0.30 plus x and x. Now guys, what do we do next? Well, we're going to write out our Ka expression, right? Would you be okay if I didn't write it? No, I don't want to do that. So we go Ka is equal to acetate. Hey. I don't know. Okay, I'm going to try this, and if it goes horribly wrong, I may cuss.
I'm gonna cross my fingers.
No, I'm still not out.
Okay.
Guess what I learned, though? Check this out. I know, I'm going there. So if you go out on the internet on Chrome, and if you don't get online, you can play a game.
I had no idea. How did you figure that out?
These guys.
I always just thought it was a cute little dinosaur.
I did too. I know. And I said, look, guy's a dinosaur. And they go hit the space bar, and it just came to life.
Like Jurassic Park. That's awesome.
Seriously changed my life.
I'm going to hope the internet goes down.
Well, here in Alpine District, you can count on it.
Interesting.
Yeah.
Sorry to interrupt. Thank you.
No. Okay. All right. So guys, let's do this. Okay. Whoa. All right. So guys, what do we do from here? Check this out. So we are going to go with our Ka 1.8 times 10 to the negative fifth, maybe. And that is going to be equal to, guys, watch how this changes now. It's no longer x squared in the numerator. It is now 0.30 plus x times x divided by 0.30 minus x. Can you imagine trying to solve this for x? But guys, we don't have to. If you remember, in our previous example, what is it that allowed us to do the squiggly equals? What's the reasoning behind it? Why did we get rid of this x? Because it's insignificant. And what does it represent? The amount of acid that fell apart. This is insignificant compared to the magnitude of the initial concentration. But now guys, watch. If this is insignificant compared to that concentration, isn't that insignificant as well? Because this is the amount that fell apart, but the amount that fell apart is equivalent to the amount of acetate ion that's formed, and it's still relative to a large concentration. And so guys, we actually get to do this. This then becomes 0.30x divided by 0.30. Nice, right? So guys, functionally what we've done, switching colors maybe so it stands out, what we've done is we've gotten rid of this and we've gotten rid of this. But now guys, look at what happens. How do we solve this for x? It's not already solved. How do we solve this for x? These cancel. Right? Why did they cancel? Because the molarities are the same. You're going to learn something very important in just a minute, so pay attention. These canceled, and what is x equal to? 1.8 times 10 to the negative fifth, which is what? Ka. So now, guys, let's do this. pH is equal to the negative log of hydrogen ion, which is equal to the negative log of 1.8 times 10 to the negative fifth, which is equal to 4 point what? 4.74. So guys, let's talk about this conceptually and then let's have the aha moment. You ready? What did we expect the pH to do as a result of the common ion effect? We expected it to go up. And if we look, we find out that in fact it did. The uncommon ion affected solution at 0.3 molar was a pH of 2.63. And with the common ion effect, it went up to 4.74. Guys, that is an increase in concentration, well, a decrease in concentration of 100-fold, right? pH is a logarithmic scale, and every change in pH of 1 is a change in concentration of 10, and that pH went from 2.6 to 4.7. That's 100 times less acidic. So do you understand the idea behind the common ion effect? But now watch this. Guys, go back and relive the math with me. Pay close attention. When we solve this for x, we got rid of the plus and minus x because those were insignificant. Then in solving this for x, the molarities canceled because they were the same. And when that happened, x just became equal to this. But what is this? This is Ka. So guys, functionally what we've done is we have plugged Ka in right here. But guys, plugging Ka in right here is actually plugging Ka in right there, and we are no longer just taking the negative log of hydrogen, we're now taking the negative log of Ka, and you learned a couple days ago the negative log of Ka has a name, pKa. So guys, the big idea is this: if the molarities are equal, then pH equals pKa. This is going to become wildly important to you in a couple days. Go ahead.
This will true with strong weak acids as well.
You have to be careful, because if the weak acid is strong enough that this is not okay, then the answer is no. Which is interesting. Okay, let's just let the cat out of the bag. Guys, that's a buffer. There you go. Guys, this thing that we just studied where we added a common ion to acetic acid, this is a buffer. We'll talk more about why it's a buffer on Monday, but guys, this is a buffer. And what you're going to find out, back to your question, Caleb, is better buffers are built from weaker electrolytes. And we'll talk more about that later. So, guys, do you understand now the idea of the common ion effect conceptually? Do you understand it mathematically? And have you wrapped your head around this magic idea that if you add enough conjugate ion salt to make the initial concentration of the salt the same as the initial concentration of the weak electrolyte, pH will equal pKa. You guys good with all of those ideas? Okay, so guys, that's where we're going to call it quits. We are going to come back on Monday, and we're going to talk about how it is that this functions as a buffer. For now, I just want to make sure that you're okay with the idea of the common ion effect. So guys, here's what we're going to do. We're going to do homework. And this is your homework. Do all of these that you can. But guys, I know this goes without saying, but I'm going to say it anyway. Guys, understand that I'm making a very purposeful decision to say, I care that my students learn this, and the best way for that to happen is to take a break. Guys, understand it would have been really easy for me to click a button and we could start talking about buffers. And if we did that, many of you would have a very frustrating weekend as you went home to try to digest all of this and then connect it to buffers. So this is me caring about you. The next 30 minutes is going to be you caring about the decision and investing in getting some homework done so that when you come in on Monday, you have a really solid understanding of the common ion effect. So go get them. The answers are not posted online, and I can't even print them. But guys, let's dig in.